Okay, so for example 2b, we have to find the highest point on the curve. So if you think about this, the highest point is kind of like a max, and so we can always find our maxes with our derivatives. And so if we're talking about the highest point, we're talking about the max in the vertical direction. So we'll be able to find that with our dy dx. Okay, so for part B, a few things that we want to remember: that dy dx is the same thing as dy dt over dx dt. And so my dy dt is just going to be 2 cosine t, and then my dx dt, using the t squared minus 5, that's just going to be 2t. Okay? And so then we could simplify this and kick this down here. And so if we cancel out our 2's, we're going to get cosine t over t, and we can call that y prime. So then we could say, well, if this is going to represent the highest point, or our max, well, then we could set it equal to 0. So cosine t over t is going to be 0. Okay? And so I might have skipped to this step kind of quickly. So let me just backtrack a second for what we know about derivatives. So if you're trying to find a max or a min, that's where your slope is 0, so your derivative is 0. So we set our first derivative equal to 0 here. So now we have to solve this. Well, if we're trying to figure out where this rational function equals 0, the value of our t isn't going to matter just as long as it's not 0. So what really is going to determine this is the fact that cosine t equals 0. And so we know that cosine t is going to be 0 when t is pi over 2. Okay, so then what we can say, so if we continue on with this, okay, so we just figured out cosine t is 0 at t equals pi over 2. And so when t is pi over 2, if we look back, we can look at the whole chart that we figured out. Our points of data, x is negative 2.53 and y is 2. So I'm pulling those numbers just from this chart right here. Pi over 2, we said x is negative 2.53, and then y is 2. Okay? So remember, whenever we're trying to find a max or a min, we also want to check our endpoints. And so for our endpoints, we would have to check at t equals 0, and then we're going to check at t equals pi. So at t equals 0, again, I'm just pulling this from the chart that we made a minute ago. X is negative 5 and y is 0, and then at t equals pi, x is going to be 4.87 and y is 0. Okay, so your max, well, your max, if we're thinking about the highest point, that's going to be our max value with respect to y, right? That's going to be our greatest y value. And so if you think about everything that we considered, we've got a y of 2, a y of 0, and another y of 0. So our max y value is right here at 2. So then we can say that the highest point on the curve is the max at t equals pi over 2, which is the point negative 2.53 negative 2.53 comma 2. Okay, so that would be your highest point on the graph. And then for part C, we have to find all the inflection points. Okay? So if we want to find our inflection points, well, we're gonna need our second derivative. Okay, so my second derivative, d squared y over dx squared, what we use for that is dy prime, so our derivative of y with respect to t over dx dt. Now, dx dt we figured out in part A, and that's just going to be, or we figured that out in part B, that's just 2t. Now, dy prime t, so what we're doing here is taking the derivative of the first derivative. So remember, our first derivative was, we simplified that to be cosine t over t. Okay, so now we want to take the derivative of this, and so this is a rational expression, so we can use our quotient rule, which we haven't used that in a while. So quick review, this is a good chance to review before the AP exam. So remember, it was low d high minus high d low all over low low. Okay, so low d high, so I'm going to have negative t sine t minus high d low, so that'll be minus cosine t, and then this will all be over low low, so everything will be over t squared. Okay, and so then we have some complex fractions that we can simplify. Well, to simplify this complex fraction, the LCM of all of my denominators is going to be a 2 t's, well, it'll be a t squared. So we could simplify everything, multiply everything by t squared. So this is going to be, let's see, up top we'll have negative t sine t minus cosine t, and then down below, if we multiply that by t squared, that's just going to give me another, that'll be 2t cubed. Okay, now, so this is our second derivative. Okay, and that's a nice mess. So what we can do to get that inflection point in that solution is we could graph that on the calculator. Okay, so let's take this down here, and we'll talk about our next step with that. So let's see. So graph that on your calculator, and when you do that, you'll see that you have a sign change at t equals 2.798386. Okay, so remember, the inflection point is going to be where your second derivative is 0, right? So inflection point, well, not where second derivative is 0, but where it changes signs. Yeah, because it could be 0, but then it could not change signs. It could go from positive 0 to positive, or negative 0 to positive, so we really want the sign change. So the inflection point is where second derivative changes sign. So we would plug in this value, and by this value I'm talking about this long one that we found right here, and then you can plug that into our original function. So you plug that in for t into your original function of x is t squared minus 5, and y is 2 sine t. So you plug that in for t into the original parametric, and you'll get an inflection point of 2.831, comma, 0.673. Okay? And then a lot of these steps you can go ahead and check me on your calculator. Okay? So that's the end of example 2. We had to find that inflection point for part C, and so that's our answer there. Alright. So the next thing that we can go over is example 3. So for example 3, we have to sketch the curve over our given interval. So our curve is x is 2 sine t, y is cosine t, over the interval from 0 to pi, and we want to indicate the direction that we're tracing it in, identify the rightmost point, and then justify that we found the rightmost point by analyzing an appropriate derivative. Okay? So, let's see. For example 3, well, we can start off by making a chart. So we're going from 0 to pi, and we could just plug in 0 and pi, but if you remember back from the very beginning of the year, we said when we're graphing parametrics, it's always good to test some value in between so we know which direction we're going in. So we'll just throw in a pi over 2. Okay? So then we have x is 2 sine t, and y is going to be cosine t. So the values of x, well, if we plug 0 into that, we're going to get 0. If we plug pi over 2 into that, we'll just get 2, and then plug pi in, we'll get another 0. So we can take these same values, plug them in into y equals cosine t. So cosine of 0 is 1, cosine of pi over 2 is 0, and then the cosine of pi is negative 1. Okay, and then we can go ahead and plot these values. So let's see. So I'll have x values. I'll have 0, comma. So my first point will be 0, comma 1, and that's about here. And then I'll have 2, comma 0, which will be here, and then 0, negative 1, which will be here. So we started here and we ended up here. And the reason why we checked pi over 2 is we could go this way, cover the left half of the graph, but we know we've got this point in the middle, so we have to be covering the right half of the graph, right? And then that's the direction that we're going in. So for our answer for part A, you would just have to show this graph right here. This is your initial point, this is your terminal point, and then you show that this is the initial and this is the terminal by having that arrow there showing what direction you're going in. Now for part B, we want to find the rightmost point. Okay, well for part B, it's easy to see that the rightmost point, we can just identify it from our graph, and that's going to be 2, comma 0. So we can just get that one from looking at the graph. But then to use the calculus with this, we want to prove that with our derivative. Okay, so a statement that we can make, our rightmost point is going to be the max value of x as a function of t. So if it's the rightmost point, you've got to think it's the maximum of x, right? We've got these parametrics in two functions. We've got x and y. X gives us our horizontal, our left and our right, and y goes up. That's our vertical. That's going to go up and down. So rightmost, we're thinking about our max of our x. Okay, so if we can take our derivative with respect to x. So dx dt, so the derivative of my x function is just going to be 2 cosine t. Okay, now we know that 2 cosine t is going to be 0 at t equals pi over 2. So we know this just from our knowledge of trig and then also from the table right up there. Okay, and so then, well, let's check this with a sign chart. So if we make a sign chart and we cover our interval, we've got 0, we've got pi, and then we've got pi over 2 in the middle. So 2 cosine t, right, from 0 to pi over 2, if you plug those values, an example, maybe if you plug in pi over 4, that's going to be positive from 0 to pi over 2. And we know that it equals 0 at pi over 2, and then from pi over 2 to pi, well, if you plug in like 3 pi over 4, 2 cosine t is going to end up being negative. So if you think about it, the function is going from being positive 0 to negative. And so you can kind of picture, if you have a function going positive 0 to negative, well, then our point of 2 comma 0 is a max, and we can say because we're finding dx dt, so the derivative of x with respect to t, this is a rightmost point, let's see, our function x of t gives us our horizontal max and min and other points. Okay, so rightmost we're thinking horizontal, so that's why we do that with our x function. So that is the end of example 3. Alright, so the next thing that we want to talk about is the arc length of a parameterized curve. So let's say we have some curve L, and that's, we can say that, or not a curve L, but let's let L be the length of a parametric curve that we're going to follow as we go from 2 points from t sub 1 to t sub 2. So L is just going to represent the distance from 2 points t sub 1 and t sub 2. So if we've got our derivative of our x function and our derivative of our y function, and they're both continuous, then we can throw them into this formula for our arc length. So it's going to be the integral, so I'll write this a little bit bigger, but you should also have the PDF of this. It's going to be the integral of t sub 1 is your lower bound, t sub 2 is your upper bound, and then the square root of dy dt, the whole thing squared, plus dx dt, the whole thing squared. Right, and we integrate that with respect to t. So we hope that we get functions that work out nicely with this. So this is just a formula that we can plug stuff into. And so then this brings us to example 4. Right, and so we have to find the length of the curve defined by x is sine t, y is cosine t, and we're going from 0 to 2 pi. So hopefully you recognize this from the beginning. If we were to square this, then this, and if, you know, x squared is sine squared t, y squared is cosine squared t, this takes us back to the example that we did in the very beginning of the topic, and this is just the unit circle. Okay, and if we're going from 0 to 2 pi, then this means that we're tracing it once completely around. Okay, and so if you think about a unit circle, the unit circle has symmetry in all 4 quadrants. Okay, so what we could do is we could find the arc length in the first quadrant and multiply that by 4, okay, to get the entire length. Okay, so our length is going to be 4 times the integral from 0 to pi over 2, right? Because if I'm doing it in the first quadrant, well, that starts at 0 and then goes to 90 degrees, which is pi over 2. And then the square root, well, the derivative, let's see, if we've got dy dt, well, our y function is cosine, so the derivative of that is going to be, derivative of cosine is negative sine, but then if you square that, that becomes a positive. So you'll have sine squared t, right? And then the derivative of sine is cosine, and we square that, plus cosine squared t dt. Now this is a nice one because this is going to work out so easily. So we've got 4 times the integral from 0 to pi over 2. Well, sine squared t plus cosine squared t is just 1, and then if we take the square root of that, well, that's also 1. So derivative of 1 with respect to t from 0 to pi over 2 is going to be 4 times t evaluated from 0 to pi over 2, and this all right here just simplifies to 2 pi. And so our answer, the length of the curve, is 2 pi. Okay, and that makes sense because if we're finding the length of this curve, we're finding our distance around a unit circle, and the circumference of a unit circle is 2 pi. So that's the end of example 4. Okay, and then the last thing that we have to go over is example 5. So we want to find the length of this curve given by x is 8 cosine t plus 8t sine t, and then we have our function for y. Y is 8 sine t minus 8t cosine t, and we're going from 0 to pi over 2. So before I go ahead with this, I would kind of like to picture what's going on here. So I might just make a really quick table and get some values. I'm going to do 0, pi over 4, and pi over 2 to see what's going on. So I'll find my x values. So my x values, if I plug these into this function here, are going to end up being 8, 10.1, and 12.6. And then my y values, so if I take these values, plug them into my y function here, they're going to be 0, 1.2, and 8. You don't have to do this, but I just want to do this just to picture what's going on. So then, if I go ahead and sketch this graph, I'll do that up here. Well, everything's positive, and so our first value, we're starting at 8, 0, and then I've got 10.1, 1.2, which I could guesstimate is about there, and then 12.6 and 8, so I could guesstimate that to be about there, right? So all I'm finding the distance of, it's just a small curve in the first quadrant. Okay, so that's not too bad. Nothing's repeating itself, nothing's symmetric, so I can just run through this formula as is. So these derivatives are going to be a whole lot of fun to do. So we're going to do these on a separate piece of paper, and then we'll come back to this piece later. Alright, so let's start off with dx dt. So dx dt, well, if our original function 8 cosine t plus 8t sine t, well, I probably should have started by writing that out. X is 8 cosine t plus 8t sine t, and so if we take dx dt of that, so to do this, let's see, we're going to need our chain rule and our product rule. So derivative of 8 cosine t, that'll give me negative 8 sine t. Okay, and then I use my product rule for this piece right here, so that'll be plus 8 sine t plus 8t cosine t. Okay, now, well, the 8 sine t's will cancel out, and so this is just 8t cosine t, and then if we square that, right, so take it and square it, and that's going to give us 64 t squared cosine squared t. Okay, and so now, let's see, we got to find dy dt. Well, remember, y is 8 sine t minus 8t cosine t. So then dy dt, running through the same process, is going to be 8 cosine t minus, alright, and then I'll throw in some parentheses so I make sure I distribute that negative correctly. And now I'm going to use my product rule on 8t cosine t, so that'll give me 8 cosine t minus 8t sine t, and so simplifying that, I'm going to have 8 cosine t minus 8 cosine t plus 8t sine t. Okay, so our 8 cosine t's go away, and so we're left with just 8t sine t, and so then if we square that, that's going to turn into 64 t squared sine squared t. So now we've got our derivative that we can plug into our integral over here. So going back to this, so we can set this up. So we're going to do the integral from 0 to pi over 2 of, we'll have 64 t squared cosine squared t plus 64 t squared sine squared t, and we're taking our integral with respect to t. Now, what we can do, our next step, well, both of these contain a 64t squared. So if I pull the 64t squared out, and if I want to pull it out of the radical, I'm going to have to take the square root of that. So then this is going to turn into the integral from 0 to pi over 2 of 8t times the square root of cosine squared t plus sine squared t. And we're going to integrate it with respect to t. Now, this just turns into 1, and the square root of 1 is 1. So now we're really just doing the integral from 0 to pi over 2 of 8t with respect to t. And so this antiderivative is going to be, let's see, antiderivative of t is going to be t squared over 2 multiplied by 8. So this is going to turn into 4t squared evaluated from 0 to pi over 2, which is just going to turn into 4 times pi over 2, the whole thing squared, which is just going to simplify to pi squared. Okay, and so then we can say that the length of the curve between 0 and pi over 2 is pi squared. And so that is the end of example 5 and topic 1.